Here we have another example of linear motion. We have a train traveling along a horizontal track, slows down uniformly at this rate until it's brought to a halt. So as a reminder, when we're talking about our linear motion, we need to decide if we need to use calculus relationships versus the kinematics, the big three. So ultimately, the question is, are we given a function, or do we know acceleration is most definitely constant? So reading through this problem, they haven't given us a function. Calculus relationships are still totally valid, but the kinematic equations, we've already gone through the calculation and the derivation of the equations, assuming constant acceleration. Reading this problem, I see that it tells me that this train is slowing down uniformly at this rate. This means acceleration is constant, which means I can use these kinematic equations. Awesome. Now, pulling those off the test notes, I'm going to go ahead and just write them here to the side so we have them to work with. We could totally write, instead of S, we could write X. Since we know this train is moving horizontally, that's totally valid. We could say X final is equal to X initial plus V initial t plus 1/2 AT squared. Whichever way you like it better, run with it. Our author just keeps them generic in terms of S, which is why I often will write it in terms of S, but X works just as well. Now, I have found it helpful, especially for those that using the kinematic equations is new for. Number one, we have to recognize that we have constant acceleration in the problem so that we know that we can use these kinematic equations. To approach problems where I know I can use the kinematic equations, to approach these problems consistently, I make a table of the symbols, the quantities that show up in these equations. So initial position, final position, we can write it as X or S. Initial and final velocity are in those equations, acceleration's in those equations, time is in those equations. I'd like to make a bit of a table and fill in what I know. If I am very careful about filling in what I know, then it will often make it easier to simplify and choose which equation we want to use. I'm going to erase the position written in terms of S simply because I've written X in my equation, or in my table rather. I don't want to think I have 4 equations, and I just have 3. Now, another good thing to do is to draw a rough sketch, because remember, when we talk about position, we need to talk about that position relative to an origin. So a rough sketch of what's going on. Here I have a train. I'm just going to draw it as a dot. I know this train. I'm going to just choose to draw my train moving to the right. You could totally draw it moving to the left. That's up to you. I know sometime later being brought to a halt means it has stopped. So the velocity at this later or final moment in time is 0. That 31 is the velocity at the initial moment in time. In order to label V initial, V final, the plus or minuses that represent the directions, I need to choose a coordinate system to work with, and I need to put that coordinate system, its origin, someplace. The nice thing is it doesn't matter where I put it. I just have to base my plus and minus signs that represent directions, I have to base those off the coordinate system I choose to use. So I find it logical to go ahead and say, hey, you know what? The x-axis is horizontal. The y-axis will be vertical, and I'm going to go ahead and choose my y-axis to pass through where the train is initially. By doing that, I'm essentially saying that the initial position of the train is 0, which is totally fine. X final would mean this distance to the right the train has moved during the time it is slowing down. It comes to a stop. We're told that in the problem. So X final, we actually don't know that. That's one of the questions it is asking. Part B is asking for that. So this is unknown. Put a little question mark in there at the moment. V initial, well, in this coordinate system I've chosen, I know my train is moving to the right, which would be positive. And we know the train is traveling at 31 meters per second initially. Now again, the positive is based off of this coordinate system I'm choosing to use. Plus means to the right in this coordinate system. V final, we know the train stops, so V final is 0. Acceleration. Well, I've chosen to the right to be the direction that the train is moving in. This train is slowing down to stop. If it's slowing down, the acceleration has to be opposite the way I've drawn the velocity. So if my velocity initially is positive, the acceleration needs to be negative, which I've drawn to the left, but I represent that in my table. I need to put that negative sign in to represent to the left. And then they've given me the number, 0.065 meters per second squared. We don't know the time. They don't tell us the time, but question A is asking us how long does it take to stop, meaning how much time does it take to stop. So we will be calculating and solving for time. So notice in this table, we don't know X final, we don't know time, but we know everything else based off of this coordinate system we're choosing. So if I come back to the equations on the right side, I know V final, I know V initial, I know acceleration. The top equation, the only thing I do not know is time. That's awesome. We're going to use this top equation to solve for time. Let's look really quickly, though, through these others. I have X final. I don't know X initial. Oh, I got that backwards. So sorry. We know X initial. I don't know X final. I know V initial. I don't know time. I know acceleration. I don't know time. So unlike the first equation, we have one unknown here in this top equation, but here in the second one, we have two unknowns, which is fine. It just means it's not going to be super helpful to start with the middle equation. The last equation, we know V final, we know V initial, we know A, we know S initial position. I guess I should make that X initial. And we don't know X final. So this last equation only has one unknown. So we can use the top equation to find time and the bottom equation to find that X position. Or once we have time, we can use the middle equation to find the X position. There's no one better than the other. But we do look to see if one of these equations is easier to use from the beginning. So let's go ahead and solve for time. A is asking us for time. How long it takes to stop means how much time. As you solve problems, I do want you to go ahead and write down the equation you are using. Don't plug numbers in yet. It's really important to be able to describe and represent, communicate the work you are doing. So, for example, if I was looking at your test, I would want to be able to see right in front of me what equation you're using, what numbers you're going to plug in, and then the work you are doing to solve for the answer. So here I'm showing the equation I'm going to use. I'm going to go ahead and put in 0 for that V final. I know V initial, I know A, so I'm going to go ahead and solve symbolically for time. As you continue through a physics degree or an engineering degree, it's really, really good to get used to solving equations symbolically. Because you keep going farther and farther, you actually will get to the point where you start programming a computer to go ahead and make solve the problems for you. This, of course, isn't terribly hard to solve, so we do it by hand. But as you continue further in physics and engineering, you'll get equations that are harder to solve by hand, and you will put your equations into the computer. So starting to practice symbolic solutions now, very important. So now I'm going to go ahead and plug in from my table. I know the velocity was positive 31 meters per second initially. The acceleration is negative 0.065 meters per second squared. Meters per second is going to cancel with the meters in one of the seconds. The negative signs are going to cancel, so I'm going to get a positive answer, which is good because time needs to be positive. And negative time would imply time travel back in time. My calculator is telling me 476.923 and some more. I'm not going to write the some more because I know my answer cannot be this accurate anyway. In order to go back, I'm going to look at the numbers given in the problem. The 31 is 2 sig figs. There's only two digits there. The 0.065 is also 2 sig figs. I tend to write things in scientific notation if I need to understand if my 0 is significant or not. That leading 0 in the decimal place is not significant. My answer, therefore, should be in terms of 2 sig figs. So I only want these first 2 digits, but I do want to consider proper rounding rules. The time in terms of 2 sig figs, because I have the 6 here, I need to round up to 480. That would be the correct answer in terms of 2 significant figures. Being given 2 significant figures in the problem implies that we cannot measure any more accurately than that. So part B. Part B, we have the option of solving this 2 ways. One of them is no better than the other. Part B, we essentially are looking for X final. How far does this train travel? So we have our train. How far does it travel during this time where it's traveling from 31 meters per second to 0 with that constant acceleration? Now that we know time, we can totally use this second equation because we know time and our only unknown would be X final. The other option would be to use the third equation and not use time. One's not better than the other. Now that we know time, the middle one looks a little better because it's already solved for X final. But there would be nothing wrong with using the third one. But I'm going to go ahead, now that we have time, I'm going to go ahead and use that middle equation simply because we have all the information we need. From my table, because of how and where I put my coordinate system, I have defined the initial position to be 0. We know the initial velocity, we know the acceleration, and we now know the time. So we're going to plug numbers in. The initial 31 meters per second. The time, I'm not going to use the rounded value of time because that will give me rounding errors as I solve for x final. So I'm going to use this longer digit and plug that in for t. And that will be the case for time in both places. And I am realizing now, sorry, that this one's not squared. I apologize for that. So v initial t, 1/2 a, this is the one that I need to square. So let's plug this into my calculator. My calculator is telling me this and so forth. I do want to think significant figures again. I totally need 2 sig figs in this answer for the same reason I needed 2 sig figs in the previous answer. So let's see, 2 digits, but talk about rounding. X final would be 7,400 meters, which we could totally write as 7.4 kilometers, or 7.4 times 10 to the 3 meters. Any of those is fine. But again, when you get to a final answer, make sure you are paying attention to significant figures and rounding appropriately. The process is what you really want to watch for here. If you know you can use the kinematic equations because the acceleration is constant, it can be very helpful to set up a table that helps us look at the equations and decide what we know and don't know, and then we can choose equations from there. There will often be multiple ways to get to the answer, which is totally fine. There's not necessarily one right way to do it. But watching signs plus or minus based off the coordinate system you choose is extremely important. As you work on homework, feel free to reach out if you have questions. I'm always happy to answer those. Send them through Canvas or set up an appointment through Zoom. I'm happy to meet with you that way as well.